And the final part of 2.3. So an example you might have on your homework is to find, drag that over. All right, find f prime of 3, given that g of 3 is 4, g prime of 3 is 2, h of 3 is 1, and h prime of 3 is negative 1. And then the function here is 3 times g of x minus g of h times h of x. So first we want to find the derivative. All right, we want to find the derivative of the function. The derivative of a constant times a function is just the constant times the derivative of that function. Here we've got a product rule. So that's u and that's v. So we've got u prime, which is g prime of x, times v, plus u times v prime. So that's h prime of x. And that's in parentheses because we have to distribute this negative. The other thing is that we want to find f prime of 3. So wherever there's an x, I'm going to plug in a 3. We have 3 times g prime of 3. I'm going to distribute this negative now. Minus g prime of 3 times h of 3 minus, distributing that negative, g of 3 times h prime of 3. And over here are the values, like g prime of 3 is 2, so that's going to go here and here. G of 3 is 4, so that's going to go here, etc. So f prime of 3 is 3 times 2 minus 2 times 1 minus 4 times negative 1. 3 times 2 is 6, minus 2 times 1 is 2, minus 4 times negative 1 is plus 4, so the answer is 8. So whatever rule they have up here, take the derivative of it. It might be a quotient rule or whatever, and then after that plug in your numbers and use these values over here. The next example might be something like they give you some kind of function, blah, 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 whatever that function is. If they want you to find the rate of change of m, what are you going to do with m? Like if it's T for temperature, or if it's P for profit, whatever equation, and they want you to find the rate of change of that equation, what are you going to do? Find the derivative of that equation. Rate of change is the derivative. Okay, that's instantaneous rate of change. If they want the average rate of change, you're just going to do plain old boring slope. If you want to find the rate at which something is growing, that again is a derivative. So those are just different ways of them that they could ask you to find the derivative. So just be aware of that. Higher order derivatives. You know, we can take a derivative of a derivative, or we could take a derivative of a derivative of a derivative. You could just keep taking derivatives as long as you want. So we already know that velocity is just the derivative of the position function. So our position function is s of t. If you take the derivative of it, that's your velocity function. Well, what if you take the derivative of your velocity function? Then technically you're taking two derivatives of s of t. So that's the notation with s double prime of t, and that's your acceleration. The acceleration is how fast something's speeding up. So that's your second derivative of the position function, and it's the first derivative of your velocity function. So s of t is the position function, v of t is the derivative of that position function. Acceleration is the derivative of velocity, or the second derivative of position. And if you're really curious, the third derivative of the position function is jerk. And if anyone's in physics, we can talk about jerk, but maybe you can figure out what that means intuitively. Alternate notations for higher order derivatives. Easy for me to say, huh? So y prime is the first derivative, y double prime is the second derivative, y triple prime is the third. Once we get to the fourth, though, we're going to do this with the 4 as the exponent, not times 4 like this. And then any nth derivative, like 20th derivative, is going to be y to that power. And that power is in parentheses, so that you know it's not really y to the fourth, it's the fourth derivative. So be aware of that distinction. First derivative here, second derivative with double prime, third derivative is triple prime, or sometimes they'll write a 3 up here, because triple prime gets to be pretty cumbersome. That's a 3. And then again, fourth derivative like this, and the nth derivative. So it's not the nth power. If it's in parentheses, it's the nth derivative. dy dx, if you want the second derivative, it's d squared y, and then over dx squared. So the squared goes here on the d, and on the bottom it goes on the x. Third derivative, etc. Fourth derivative, same thing here. We don't need the parentheses because the d is obviously the derivative, right? And the nth derivative. It's being slow here. Nth derivative. Sorry, that's an n. These aren't used very often, but if you want the second derivative of this function, and that is a subscript, it should be down here. Second derivative, third derivative, etc. I think you can figure out that pattern. And here again, the f of x is just like the y on in the example to the left. So we'd have that, and then the third derivative like this. So we don't use those very often, but these we use a lot. So be aware of these for sure. Oh, by the way, that's on page 125 if you want to look at that. All right. One of the things on your mark is going to be to graph the first and second derivative of a given function. So we've talked about how to graph the first derivative. Remember, you pick a point like, okay, at -2, approximately what is the slope of that? 2, 3, 4, 5, 6, 7, 8. At -1, so about right here, right? -1. It's still kind of steep, but maybe -4. So -1, -4. At 0, the slope is 0. And again, at 1, it's going to be 4. And at 2, just keep symmetry there, it's going to be 8. So it's kind of like this. All right, that's the first derivative. Okay, what would the second derivative look like? Well, the second derivative, I wish I could change my pen color here. Oh, I can. All right. Second derivative is the derivative of this. So at -2, we've got a pretty positive value, right? So at -2, we're positive, maybe 8 again. -1, less steep, but still positive, so maybe 4. At 0, less steep, maybe like 1. I mean, at 0, it's 1, yeah. And then at 1, it's getting steeper again, so we'll say it's that. And then at 2, it's steeper again. So the blue line is the second derivative. So these are approximate. I just want the kind of shape. So we're going from this shape to kind of an S curve and then back to this shape. All right, let's look at this graph. Like at -3, we have a pretty steep. -2, less steep, but still pretty steep. So maybe 5. At -1, it looks 0, it's negative. So maybe -4, I don't know. So this is at 0, -4 maybe. And then at 1, it's 0 again. And then at 2, pretty steep positive, almost like this one over here. So let's say it's here. And at 3, it's up here. So we'll go with some symmetry here. Looks like we're going like this. So bad line, Lammers. Anyway, so like a parabola, right? Let's draw that. So the blue one is the first derivative. Now let's draw in the second derivative in green. So we want the derivatives of these. So at -3, it's negative, pretty steep, so maybe like here. And then at -2, less steep, so maybe here. And at -1, it's getting less steep, so maybe here. And at 0, it was flat. It would help if you have a really good line for your parabola. My computer doesn't let me draw very straight lines sometimes. And at 1, it's about a 1 or a 3 or something, and then it's steeper up here, So as you can see, my line's going, again, that's supposed to be a straight line. It's kind of, these are just approximations, but you can see that knowing what you know about derivatives, what's the power of this function right here? It should be something to the third, like x to the third with some other weird stuff after it, right? When you take the derivative of that, you know the derivative is going to be 3x squared, or maybe if this were a 5, it'd be 15x squared, whatever. It's going to have an x squared in it, right? So the first derivative is going to be something x squared, so parabola, right? And then the second derivative is the derivative of x squared. So that 2 is going to come down, and what's going to be the power of that? It's going to be something x, so a straight line. So even if they don't give you the function equation, you should still be able to know that the derivatives are going to decrease in power, and it should give you an idea of what that graph should look like, in addition to picking out the individual tangent lines. All right. One last thing is, on the homework it'll say verify that the function satisfies the differential equation. A differential equation is the differential equation. When you're in college, you're going to take a whole class called differential equations, possibly if you major in math. So they're saying, does this equation satisfy this? Well, to do this, we need a second derivative, and then we're going to need the original function. So this original function here is going to go here, and then we're going to take the second derivative, so we got to get through the first derivative and get to the second derivative, and that second derivative is going to go here. And what we're going to do is fill them in and see if it equals 0. That's what satisfying the differential equation means. So first derivative, 3 times the derivative of cosine, it's negative sine, so I'm going to write negative 3 sine x, and the derivative of sine is cosine. And now take the derivative of that. The derivative of negative 3 sine x is negative 3 cosine x. And the derivative of cosine x is negative sine x. So there's my second derivative. So I'm going to plug that in here. So negative 3 cosine x minus sine x plus, and then plug in y, 3 cosine x plus sine x. Does that really equal 0? Of course it does, because these add up to 0 and these add up to 0. So our answer for this one is yes. But if it didn't equal what it said it was supposed to equal, then your answer would be no. Just use whatever differential equation they give you and whatever function they give you, using whatever they have in here to decide how many derivatives you need. And there's your homework. Page 127, 77 to 87 odd, 93 to 117 odd, 127, and looks like I forgot my comma, 129.